Another new derivative rule, the derivative of exponential functions. So an exponential function is an equation where the variable is in the exponent. So we're going to determine the derivative of y equals a to the x. So a is some number, could be 2 to the x, 5 to the x, 10 to the x. And if anyone's tempted to use the power rule, say, well, why can't we just bring down the exponent, lower the power by 1? That's the rule when you have variable to number. We have number to variable. These are very different. Number versus variable, variable versus number. So the power rule applies to functions of this form. We do not yet know the derivative for functions of this form. So we could go to the definition, or because we know the rules for the derivatives of logarithms, we could take the log of both sides. You're allowed to take the log of any base you want, so I'm going to choose e, because we know that that derivative is simpler than any other. So we're taking the ln of both sides. So that's simply log base e of both sides of the equation. We're allowed to take that exponent and bring it down. That's one of our laws of logarithms. And then we'll take the derivative of both sides of the equation. This one will be using implicit differentiation. The derivative of the ln of an argument is 1 over the argument. Derivative of the argument is dy dx. This side is not so obvious. We could think of this as a product rule. Derivative of first is 1 times the second, so that explains that term. And then if we try to do the first times the derivative of the second ln a, where a is a number, means you're taking a number and calculating the ln. So take a number, calculate the ln. If you put that in your calculator, you get a number. It's not a variable. And so the derivative of ln a is 0. So if we try the product rule, derivative of first times second plus first times derivative of second, the derivative of the second is 0. So that's why there's nothing else here. Another way of thinking of this is just a number times x, so the derivative is just the number. Let's clean this up. If we multiplied both sides by y, that would get rid of this fraction and put the y on the other side. And then instead of having a derivative with y in it, we can replace that with a to the x. So the derivative of a to the x is a to the x. So what you started with appears in the answer, and then multiply by the ln of whatever your base is. For example, if we take the derivative of 5 to the x, we're just putting 5 in place of a, so we should get 5 to the x ln 5, and we do. Again, what we did, derivative of 5 to the x, we're putting it in using this rule. Derivative of a to the x is a to the x ln a. So 5 to the x would be 5 to the x ln 5. And once again, is there a base that would make this expression more simple? The ln of what can we evaluate? So the answer is e. So if you take y equals e to the x, let's use our rule. The derivative is going to be e to the x ln e. And ln e, ln is base e, so what exponent goes on e to give you e? That answer is 1. And look at that. The derivative of e to the x is e to the x. Absolute magic. So if you were to graph e to the x, it's an exponential function. If you found the slope of the tangent and plotted all those points, you'd end up with the exact same graph. Glorious. So we'll do this again just so you understand where it came from. Derivative of e to the x, we're applying this rule. We're replacing the a with an e. So the derivative is e to the x ln e. What exponent goes on e to give you e? That answer is 1. So the ln of e is 1, and the derivative of e to the x is exactly what you started. So let's apply that. The derivative of e to the x squared plus 5x plus 1 is exactly what you started with, and I think we're expecting this term. We have to use the chain rule. We're taking the derivative with respect to x, so we're taking the derivative of the exponent. Derivative of the exponent, derivative of x squared is 2x, derivative of 5x is 5, derivative of 1 is 0. For those who are asking, why did we not see this term up here? When you take the derivative of e to the x, you get exactly what you started with, multiplied by the derivative of the exponent, which in this case is 1. Taking the derivative of e to the x squared plus 5x plus 1, exactly what you started with, times derivative of exponent. We tend to clean it out by moving the simpler term to the front. And that's a common mathematical idea, that you tend to go from simple to complex. All right, you try this one. Derivative of e to the sine x. You write down exactly what you started with and then multiply by the derivative of the exponent. So e to the sine x gets written down. Derivative of sine is cosine. And we learned that instead of putting the second term here, we tend to move it. So we just do that right away. Exactly what you started with, derivative of exponent. Do some more. The derivative of x squared plus e to the x squared to the 5. Now, if anyone is tempted to move this like we did when we did the logarithms, we cannot do that. That was a law of logarithms. There are no logarithms here, so we have to do a chain rule. The chain rule, you remember, bring the 5 down, leave the bracket alone, lower the power by 1, multiply by the derivative of what's inside. Bring the 5 down, leave the bracket alone, lower the power by 1. Derivative of what's inside, derivative of e of x squared is 2x. Derivative of e to the x squared, that's our new rule. You write down what we started with, and then you multiply by the derivative of the exponent. The chain rule, bring the 5 down, leave the bracket alone, lower the power by 1, multiply by the derivative of what's inside. Derivative of x squared is 2x. E to the x squared is this new rule where you write down what you started with and multiply by the derivative of the exponent. So we write down what we started with, and the derivative of the exponent was 2x. Let's do another one. The quotient rule. Again, for those who are tempted to clean that out, simplify it like we did when we had logarithms, we don't have logarithms, so we have to do a quotient rule. The quotient rule, derivative of top times bottom minus top, derivative of bottom over bottom squared. The derivative of the top is the new rule. We're going to write down what we started with and multiply by the derivative of the exponent. So write down what we started with, derivative of exponent. So derivative of top times bottom minus top times derivative of bottom, the new rule, write down what we started with, multiply by derivative of exponent, all over bottom squared. Let's do that again. It's a quotient rule, derivative of the top. The new rule, write down what you started with, multiply by derivative of exponent. Derivative of top times bottom minus top, derivative of bottom, the new rule, write down what you started with, multiply by derivative of exponent. All divided by bottom squared. Now we tend to clean these out by multiplying these terms in. We do that because of the minus sign. It'll allow us to collect some like terms. So 3 e to the 3x times e to the 3x. Remember, you're adding your exponents. So that becomes 3 e to the 6x. 3 e to the 3x times minus 1. Minus 3 e to the 3x times e to the 3x. Add your exponents. There's another 3 e to the 6x. And minus 3 e to the 3x times 1. I think we have some like terms here. The 3 e to the 6x minus 3 e to the 6x, those will be gone. And minus 3 e to the 3x minus another 3 e to the 3x gives us minus 6 e to the 3x. All divided by e to the 3x minus 1 squared. Your job today, we're still on page 1. Today we're doing part B. Once again, there will be some really interesting simplification questions. So if you get an answer and you're unsure of how I got mine, just let me know and I'll be happy to explain.